So here's a bunch of covers just as examples to work with. We constructed all this to be able to get lots of examples. I mean, we constructed a free group, which is important, of course, this space X. Here lots of covers. So remember, to construct a cover, we just needed to construct a graph that covers it. Indeed, we'll see that any cover of a graph is a graph. And we needed to construct a graph morphism, which is easy to verify. And this was our old friend, the universal cover. Okay. So here is an interesting example. I unwrap the alphas and leave the betas alone. So I can map from here to here by simply mapping, of course, alphas to alphas and betas to betas. And the maps are obvious. They're the graph maps. So this is a cover in only one direction. Okay. Another interesting infinite example is the lattice. So this is contained in R squared. Okay. And the inverse image of x0 are just the integer points. So P inverse of x0 is going to be z squared. And lattice points are joined by horizontal lines, which are alphas, and vertical lines, which are betas. Or if you're going in the opposite direction, alpha bars and beta bars. Okay, so that's kind of clear. So you have the point 0, 0. And it forms a covering map of this. This is an interesting thing because you see it has lots of loops. Okay. It also has a lot of symmetry. It has a symmetry group which is z squared. This is one of the things I mentioned last time, that there was a lot of symmetries we're going to understand. Okay, and here are some finite examples. I can unwrap alpha instead of fully just into 3 loops. Okay, so here this one goes to this, into 3 loops. And here what I did is unwrapped it into 3 loops, and then a beta I unwrapped into 2, and then alpha again. Well, this point has to be 4-valent, so I have to have an alpha, but this time I'll take a non-unwrapped. This, you see, is a little less symmetric. In fact, it doesn't have any symmetry. The reflection looks like a symmetry, but that doesn't respect the covering map. Okay, so this is an example where you really don't have, which is important. And here's another non-symmetric example. So here what we did is we have kept beta alone, or you could keep alpha alone, and unwrapped completely. So this is somewhat similar to this. So vertices, so here are vertices. Well, what are they? So vertices are reduced words, but they do not start with beta or beta bar. So you take all reduced words which don't start with beta and beta bar and have edges similar as we did in the universal cover that we had constructed. So this will give you a cover. Now this will deformation retract to a single loop. So its fundamental group is Z. So this is the subgroup. In fact, so here the subgroup is going to be beta contained in alpha beta of this. Here it will be not beta just, but all its conjugates. So this is not an abelian group. Okay. Here the loop group we will see a little later. It's a kernel of the abelianization map. Okay. So all these are important examples. Here the fundamental group is of course trivial of x tilde in this case. So we saw a bunch of examples here just for having a lot of examples of covers. So you see some have more or less symmetry. Okay. Now we are going to exploit our based covers to try to understand this better. But before that, let's just look at one aspect of this, which is a fiber of a point. You see, some of these are finite covers and some are infinite covers. What I mean by that is if I took x0, or indeed I took any other point x, x0 is a bit special in this example, so let's just take some other point x and look at the inverse image. Over here I'll get 3 points. This one here. Here I get infinitely many points. Okay. And here I get a bunch of points. Here's an alpha, here's an alpha, here's an alpha, and there's an alpha here as well. Similarly, here we get infinitely many points, one for each alpha edge, etc. Okay. So as a set or a space, this is not very interesting. It's either a finite set, hence determined by its cardinality, or an infinite set, and infinite case countable infinite in all our examples, and indeed in all connected covers, but because of the discrete topology, the set determines the space. Nevertheless, to construct the cover, we want to know the fiber in a nicer way, which is what we will see next. Okay, and for that we can work with any of these examples. We'll work with one of them and see how we can identify the fiber. But since one-dimensional pictures are not as easy to see as two-dimensional ones, let's look at this space instead. Okay. It's a nice exercise to go back to the one-dimensional pictures and see what we have. So this is R cross S1 and this is S1 cross S1, and in the first coordinate we are mapping by simply, so the map here is going to be, it will take a t comma theta, let's say, to e to the 2 pi I t. Theta, it's an unwrapping the torus in one direction, as not in the other direction. Okay, so let's try to understand a fiber. It's an infinite fiber, but what we have is the following situation. We have P goes from y0 to x0. Okay, and P star of pi 1 of y0. The image, remember, is injective, so you can really identify it with pi 1 y0, is contained in pi 1 of x0. Let's call this G, and let's call it by definition, and let's call this H. So we have two subgroups H and G, and we want to know how the fiber is determined by H and G. And this is in a rather nice way. Let's take another point Y in the fiber and pick a path joining these two. I could take the straight path, but I'm perversely going to take a path which goes here because I don't want to be misled by our example. So what happens to this path? So let's dash it a little bit. Well, remember y0 and y both go to x0. So if I took a path like this, it will go to a path which is something like this. This is not geometrically very accurate, but the key point is that you get a loop. Okay, so we have a fiber, so can be defined in the following way. So suppose we are given y inside P inverse of, let's say, x0, the base fiber. Okay, then y0 to y. So we pick, let's call it alpha from y0 to y. Okay, then what we have is we are going to get P composed with alpha. Alpha itself is not a loop, so it's not an element in any fundamental group. But P composed with alpha is a loop. So this belongs to pi 1 of x0. Okay, but note alpha is not a loop, so this may not belong to H. This belongs to G. Indeed, it usually doesn't belong to H. Okay, but then what we need is dependence of alpha. If beta is another path. Let's look at our picture here again. Let's take an orange path from here to here. Okay, and then perhaps this orange path is a loop like this from here to here. Okay, it's a different path which goes from here to here. Okay, so what do we know formally then? What we know is that, so beta is another path. Well, we can think of beta as the following. It's alpha, but before that I can look at beta star alpha bar. Okay, and the key point is this is a loop at y0. Okay, and therefore if I look at P composed with beta, okay, so this is going to be P composed with beta star alpha bar, or perhaps I should write in okay, it's all right. It's maybe I should write it in homotopy notation because not everything is a loop, so we won't say equivalence class. Let's say P composed with beta is homotopic to P composed with beta star alpha bar star P composed with, so this is the one term, alpha. Okay, so the class of P composed with beta is the same as the class of P composed with alpha and multiplied by, well, the key point is this is a loop. B star alpha bar is a loop. Okay, so this is going to be P star of the loop beta star alpha bar, and this is an element in H. Again, no magic happened here. What happened is to note that if I take the difference between the two paths is a loop, so you can think of the new path beta as itself followed by the inverse of the old path and then the old path. But the first two together form a loop at y0. So their image are in this loop group hg. Okay. So what you know is, suppose we call this g prime and suppose we call this g. Okay. So thus what we know is g prime is h times g. Okay. That is, we get a well-defined right coset. Okay. And indeed the converse is also true. Okay. So namely that if we have if we have 2 points which are in the, which give you the same right coset, they are the same point in the fiber. So what we have is, we have a map from P inverse of x0 to the right coset space, G over H, or maybe it should have been, or maybe I should write it this way, okay, as right coset space, and we can construct an inverse map. I won't verify it's an inverse, but I'll verify that it's well defined. That it's an inverse will be absolutely clear. Namely, so suppose we have G. So we are given G in G. Okay. And so G is going to be alpha. Okay. So we have a map. Let's give this a name, phi. Okay. So define C of not just G, but its entire right coset, and we'll later show it's well defined, C of hg to be alpha tilde of 1. This is our usual construction. We take a loop, look at its lift, and look at the right end point of that lift. Okay, so here we have, now if g prime is also in hg, okay, that is g prime is going to be equal to some h times g. Okay, then we can pick a representative of g prime. By the way, we know the endpoint doesn't depend on choice of representatives, so I'll just assume we chose this. Okay, so let's pick a representative. Assume this is lambda. Okay, and assume this is alpha. So then g prime is the class of lambda star alpha. Okay, so lambda belongs to p star of pi 1 of y0. Okay, so claim here is that lambda tilde of 1 is going to be equal to y0 itself. That is, lambda tilde lifts to a loop. Okay, so that is what we have to see next. And this is simply true by definition, okay, because lambda belongs to, so I should be careful here. Let me say class of lambda belongs to this. Okay, so that implies that lambda is homotopic to P composed with lambda prime, or maybe I should give it another thing to emphasize its eta prime, or eta, where eta is a loop at y0. Okay, therefore lambda tilde of 1 is going to be equal to eta tilde of 1. But eta tilde of 1, because we know that if two sorry, I said eta tilde, simply eta of 1. Why is that? Because as eta is just the lift of eta tilde, P composed with eta tilde beginning at 0, but eta is a loop, so this is just y0. Okay, so we are nice. So what we have here is, recall that g prime is represented by lambda star alpha. Okay, and lambda tilde of 1 is 1. Therefore lambda star alpha tilde is going to be equal at 1 is going to, well, I will put at 1 later. This is simply lambda tilde star alpha tilde. This doesn't always happen because these are not well defined, but lambda tilde is a loop, so it ends at y0. So this product is well defined. So this implies that lambda star alpha tilde 1 is just lambda tilde star alpha tilde of 1, which is just alpha tilde of 1. So what all these have established is that if I look at image, so that is C of G prime is C of G. Okay. So C of HG prime is C of HG. So okay, this is bad notation. I should have defined it on G and showed that you get an induced map on the quotient. But modulo that, what we have seen is that if I took a different choice of coset representative, I will get the same lift. Okay, now if you look at this and the previous construction, they are obviously inverses of each other. In the previous construction, we took a path upstairs, pushed it down, and looked at the element in the right coset. Here we took a path downstairs for after choosing an element in the right coset, lifted it up and looked at the right end point. So these are obviously inverses of each other, hence their bijections. Okay, so this tells us that given G and H, we actually have a fair grip on the cover. We know the fiber over each point. Okay, but of course the inverse image of each point is discrete. If we just put them together as a union, you will get a horrible space. Instead, what you have to do is, given nearby points, you will still want to look at the inverse image. You would want to look at fibers being coordinated in some appropriate sense. You want to put the topology. You can't always do that. That depends on hypothesis. But we will come to that when we turn to constructing the covers. But now what we have done is we have seen some nice examples, and along with seeing some nice examples, we have managed to see what the fiber of a point is, and hence we see a somewhat algebraic description of the space in terms of the fundamental groups.